myself Satyajit Puhan, working under Dr. Harnindaya at National Institute of Technology, Jalandhar. The title of my talk is the structural analysis of pion and cation with distribution functions like TMDs, GPDs, and GDS. These are the outlines of my talk. First, I will go briefly on introduction. Then I will little bit talk about pion and cation. Then I will talk about the TMDs up to twist 4, and then PDFs, then GPDs, and then GDS. As already many speakers has told about the introduction part, like why we are dealing with the quark and gluon structure. So I have to skip this part. Like hadrons are made up of quark and gluons by strong interaction QCD, and we generally study how the quarks and gluons are distributed inside a hadron. To study these functions, we need structure functions like GTMDs, TMDs, GPDs, and PDFs. And these are why we are studying these structure functions. Okay. One of the structure function is PDF, which gives us the 1D structure of a hadron, and it carries the information about longitudinal momentum fraction x. It can be extracted from DIS experiment. And while TMD and GPD have the structure of 3D structure, TMD carry the information about longitudinal momentum fraction and transverse distribution of the quark. And TMD can be extracted from Dranian process, Dranian process like this, and SIDS process. GPDs provide the 3D structure, carry the information about longitudinal momentum fraction and Spartan distribution like zeta and delta. It can be extracted from DBCS and DBMP. While GTMD carry the information about longitudinal momentum fraction, transverse distribution, and Spartan distribution with 1 degree of freedom. It can be extracted from Dranian process. To study these structure functions, we generally use the These structure functions are related to each other by this diagram. If one can get the GTMD, he can get every structure function like GPD, TMDs, TMSD, and form factors, PDFs. Like these are the kinematic variable I am going to use in the next slides. To study these distribution functions, we use the neutron dynamics. These are the coordinate system of the neutron dynamics, the right side. And this is the quantization system. Frame, my mistake. Okay, why neutron? These are the advantages of neutron, like it has a simple vacuum state, boost invariant frame independent wave function, and no square root in Hamiltonian, and maximum number of kinematic variables. Okay. In this talk, I am talking about pion and cation structure. That is, pion is a bound state of U quark and anti-quark D, having mass about 140 MeV, existing if only the mass is dynamically generated. While in the case of cation, it is a bound state of U quark and S anti-quark, having mass about 490 MeV. To study pion and cation structure, EIC and compass, EIC and compass will give a structure about the quark and gluon contribution to the mass and the internal structure through a Sullivan process. You can check out these two papers, they are very interesting papers, how they are going to study the pion and cation structure at EIC. This is the diagram of the Sullivan process to prove the structure of cation. Okay, in this talk, I am going to talk about something which of our paper which have recently accepted in JR. In case of spin zero particles, there are total 8 TMDs up to twist 4, which can be expressed in the quark-quark coordinator as this coordinator. Here psi k is the neutron bound state of pion and cation, with psi is the quark field operator, and gamma is gamma matrix, and W is the Unson line. In this case, we are taking Unson line as unity. These are odd TMDs. In case of twist 2, there is one T even and another is T odd. In case of twist 3, there are another 2 even and twist 4 another T even, like this. On these T in TMDs are unpolarized quark distributions. Okay. These TMDs are related with each other by some equation of motion, which we have verified for these above three are for T in TMDs, while the lower three are for T or TMDs. In this work, I have used night front quark model and night front holographic model. In both the model, there is no gluon contribution in the Fock state, so I can't calculate the Tinda terms. This is night front quark model. Here, the meson state is represented with different Henry-Cities function by this equation, where psi sz is the spin improved meson wave function, which can be given as this into momentum space wave function. This is momentum space wave function, and these are the spin wave function for different Henry-Cities, with omega and omega 2 having the form of this, depend upon the quark masses and transverse momenta of the quark. The needing twist, this is the F1Q is calculated in the overlap form of different Henry-Cities of wave function in the form of this. This is for up Henry-Cities, this is down, this is down up, this is down up down, and the form comes like this. And in case of night front holographic model, we have used the Barbara-Pasquinis model, which is the combination of nz equal to 0 state and nz equal to 1 state quark orbital angular momentum. And for nz equal to 0 state, the bound state looks like this, and for nz equal to 1, the bound state looks like this. Okay. There is another thing. This psi have a psi 0 and psi 1 have different form for nz equal to 0 and nz equal to 1. They can be written like this. And this is our momentum space wave function. And the overlap form of needing twist TMDs in night front holographic model is found to be this. And the form of TMD found to be this, where kappa is the ADS-QCD scale parameter, which is fixed with mass spectra of pion and cation. In this calculation, we have taken two variables like quark masses and, two input parameters like kappa and quark masses. For night front holographic model, for night front quark model, we have taken beta and quark masses as our input parameters. These are the 3D plots we have got from our result. This is for Pion F1Q U quark, this is EQ, this is F perf, and this is F3. If you see the factor 1 by x in EQ and F per Q shifted the distribution towards the lower x value, similar to that of F3, twist for TMDs. This is the Pion U quark in night front holographic model. This is there are two peaks formed due to the combination of nz equal to 0 state and nz equal to 1 state. Similar kind of behavior you can see for EQX, F perp x, and F3x due to the factor of 1 by x square in high twist TMDs. This is Cation U quark. In case of Cation, there are two quarks like U quark and S quark. U quark carry having less quark masses, while S quark carry more quark masses than U quark. And due to this, the distribution shifts towards the lower x value. These are the both model comparison for Pion U quark TMDs. The red lines are for night front holographic model, and the black dotted lines are for night front quark model. They have similar kind of behavior in both the models. Okay, then I have calculated the average transverse momenta and the Gaussian transverse dependence ratio RG for both the models. If you can see, in case of needing twist TMDs, that is F1, it carry highest longitudinal momentum fraction than the higher order twist. Similar kind of behavior you can see night front holographic model, but in case of night front constitute model, they F3 carry the highest longitudinal momentum fraction. And this is the BLFQ result. This is the Pion average momenta for U quark and S bar quark. Here RG is an interesting factor to check our modern dependence in Gaussian dependence of our modern, and this is coming like 5% error from unity. These are the quark densities which I have noted for U quark of F1Q in right front holographic model. You can see at x equal to 0.6, all the nodes are concentrating around x equal to 0. As it is an unpolarized TMD, it should look like this, and there are more density for x equal to 0 at center, x equal to 0.5 or 0.6. Okay. Then I have calculated the pattern distribution functions by integrating the TMDs over Kuiper, transverse momenta of the quark. For needing twist TMDs, it is F1Q, and for subneeding, it is EQX and F perp x, while the twist for, I have done it for just academic purpose, nothing for else. And they obey the PDF sum rule, right? F1x should be, the sum of dx F1x should be equal to 1, quark anti-quark x momenta should be equal to 1, and dx EQX equal to sigma by mq, sigma by m, where m is the quark masses, and sigma is the hadron masses by 2 vector. And I have also checked the quark model Lorentz invariance relation, which are satisfied by the PDFs. These are the PDF relation for both the models, right front holographic model and right front quark model. Both the models have the similar kind of behavior. But this is for Pion U quark PDF, this is for Pion S anti-quark PDF. Now I have compared my PDF data with experimental results. Like I have compared the unpolarized PDF XF1X with E615 data and E61 modified data. These data are evolved from 0.22 modern scale to 16 GB modern scale for this, and they are similar kind of behavior with the experimental data. They are slightly deviated from the E615 data, but they have exactly same behavior with E615 modified data. I have taken the both modern scale to 0.22. I have not changed for different models. And this is the Pion to Pion ratio data. You can see our results starting from 1.2 and vanishes at around 0.9. This is because our Pion U quark model, both the models have zero distribution around 0.2 to 1. That's why they are coming like this. But we have to check that in our model, why it is happening. These data have been taken from E615 and JS Conway data and MICHOS data. These are our prediction for Pion U quark and Pion S bar quark, which has been evolved from 0.22 GB square to 20 GB square in both the models. Another thing I forget to tell, we have done this calculation in next to needing order PDF dignap evolution. Okay, ongoing compass and amber data will provide more information about pattern distribution functions and pattern distribution amplitude. These are the average X value we have calculated for all the TMDs. You can see the needing twist PDF carry highest average X value, then the subneeding twist, then the higher order twist. That means at non-perturbative region, we have to consider the higher twist contribution to the scattering cross section. And in case of Pion, due to the heavy masses of S quark, it carry highest longitudinal momentum fraction than the U quark. We have also compared our data at different energy scale, that is 4 GB square, 5.76 GB square, 20 GB square with lattice data and other modern data. They are found to be similar. Now I should talk about GPDs. In case of spin zero particles, there is only one GPDs at the needing twist, which can be overlapped which can be overlapped in the form of this at non-zero skewness, where x double prime is the momentum carried by the quark, which can be given as x plus zeta by 1 plus zeta, and x prime, that quark going into the hadron, which carry the momentum fraction x minus zeta by 1 minus zeta with transverse momenta like this. For more details, you can check out PRD 100 Satvir ma'am's paper in night-cone quark model and Navdeep ma'am's paper in night-cone holographic model for different symmetric and asymmetric approach. These are the electromagnetic form factors have been extracted from our GPDs. You can see our model quite give more accurate result. It have similar trend with the experimental result in the region of 0 to 0.5. But after that, these are the lattice QCD data. They are going slightly up with the lattice QCD data. This is for Pion data and this is for Pion data. For Pion data, we have not included the lattice QCD data, but we have matches with the experimental data. This is the Pion to Pion form factor ratio, and they matches with the experimental data. The data is very old. Okay, another interesting distribution function anyone can study, that is generalized distribution amplitude. That means gamma star goes to 2 Pion process or 2 hadron process. Like it can goes to pi minus pi plus or pi naught pi naught. Okay, GDA as the TS crossing of DBCS process, the coordination of the GDA is given by this. In case of GPD, you found there is another hadron state at the initial state, but in case of GDA, there are 2 hadron states at the final state. And the coordination given by this with the kinematic variable Z equal to K plus by P plus, zeta equal to P plus by capital P plus, W square is equal to center of mass energy. This is the diagrammatic for GPDs. This is our for GDA. Currently, I am collaborating to calculate the GDA. We have some data, but I can't show them. Okay. There have been some theoretical extraction of TMDs and PDFs have been observed. These are map collaboration and Vladimir's Pion-induced Dendron process with TMD factorization. There is another paper just come this week for Pion PDFs. Thank you to every professor for the helpful discussion and during the school and workshop. Thank you.
I have a curiosity. Can you go back and when you started showing the 3D plots of your TMDs? No, go back here. Okay. So this is Pion U quark. Okay. So the upper row I see on the left F1, and which is the only leading twist object. Yes. Right? Now, on the right there is E, which is twist 3, and yes. Then below in the lower row, F perp, which is twist 3, and F3, which is twist 4. Now, what I don't understand is that if you look at the lower row, the scale of the z-axis is much larger than the other one, the other plots in the upper row. And I would expect that twist 3 and the twist 4 objects are much smaller than the twist 2 one. So did you, yeah, you see that, yeah, you have
this is due to the momentum fraction. They came with the factor of 1 by x. If you go to the lower x, then it will be multiplied by 0.1, that will go to 10 times the leading twist.
Wait a minute. So you mean that the limit for x going to 0 of these objects goes like 1 or a power of 1 over x? Yeah, okay, but I see that this trend is there since already for very large, quote, large values of x. I mean, you see, look, for example, F perp, yes. The corner, lower left corner. Yes. You see that this surface is already at 10, 20, 30, when x is still in the valence domain.
Okay, okay.
I would expect that this is much, the peak is much narrow, because I would, from that plot, I deduced that the twist 3 object is much larger than the twist 2 1, which is not something very reasonable.
Okay, similar kind of behavior have also shown in the night front constituent model by Barbara Pasquini and Cedric Norris. The similar kind of behavior. I don't have a proper explanation to it, but I will look into it.
I have one question, which is maybe you mentioned it, but I maybe didn't pay attention enough. How do you set the model scale?
Model scale?
Yes. How do you decide what is the model scale?
Okay. Okay. We just take a initial model scan from previous calculation. There have been model scan around 0.20, 0.246. Not a stable model scan for night quark model for 2 feet hour.
So it's based on previous literature?
No.
Oh, sorry.
When we use that model scan, the peak are coming like this goes like this, sometimes this comes like this.
Yeah, but how do you fix the model scale to be 0.2? You said 0.2 GV, right?
0.22 GV.
Why do you choose 0.2 GV?
Yeah, I asked Radici about this, why we have not a certain modern scale. And he said that you have to change your modern scale times to time to compare your data with experimental data.
Okay, so in principle, you should look for the best initial model scale to reproduce data in the best way. Yeah, that would be a good idea, but you didn't do it yet. Now you choose 0.2 based on the feeling that it's okay. Okay, thank you. And also concerning the average transverse momenta, you get something like 0.2 something, I guess. Yeah, these ones. So we have from the extractions, from the map extraction, we have something like 0.47 for Kepler squared. Kepler squared.
Okay.
Average Kepler squared.
Average Kepler square.
Yeah. So this may be still okay in the sense that it's at a higher scale than your model. So, and probably evolution, TMD evolution will increase the K-perp, but yeah, you can compare it to the phenomenology.
I tried to evolve our TMDs, but unfortunately at x equal to 0.01, your extraction is like at 2 or 3, but my evolution are coming around 0.7 and 0.8. I don't know why this.
We can check it. And also, your K-perp is x-dependent or not?
K-perp, no.
The K-perp, the average K-per square, can change with x or not? You're integrating over x, but it changes with x.
Yes. Yeah. Yes.
Because our extraction is 0.47 at x equals 0.1, and it can be different in other values of x. Yes. So this also has to be taken into account.
Okay.